Hey there guys. So in this video I'm going to prove the volume of a sphere, which is 4/3 pi r cubed, and we're going to prove this using integration like we just discussed in class, using this idea of volume being the integral of the area from of a cross section from one bound to the next. Okay, it's going to get a little complicated here, so take your time watching this thing, and as always, let me know if you guys have questions. Okay, all right. So so this is our goal, right? We want to get there, and let's kind of draw a picture to get a better idea of what's going on here, right? So I'm gonna actually make this a little large. All right, so I have a sphere. All right, and this sphere is actually centered at the origin. Now, it's important for us to know what's changing, what's not, as we go from left to right and integrate this thing. So how are we going to do this? I'm going to first off integrate this from left to right. So imagine that the middle of the sphere is at the origin. I know it doesn't really look like that because my drawings are not good, but imagine that we're going from left to right and we're integrating this with knowing that the cross sections are circles, right? So if I were to draw one of the cross sections, like right here, let's say, right? Imagine that this cross section has like some width, which of course is the dx part, right? And then here's the rest of the circle. We have to identify a couple things that are going on here, right? So first and foremost, if we want to use this formula, volume is equal to integral of a of x dx, we got to figure out, well, what is my a of x formula going to be on this one, and in addition, what are my bounds going to be, right? So I think we should start with the bounds because that's pretty easy to figure out. If you think about it, 4/3 pi, I'm going to use a capital R. This is the known volume of a sphere with a where the sphere is capital R. And in this problem, that capital R, for the radius of the sphere, doesn't change. It's going to be the same no matter where you are in the sphere. So we're going to label the bounds from -r to r. Okay? Now, the reason why I made it a capital R is because we're going to use the lowercase r for the radius of our cross section. So that's this blue guy right here. I'm going to call that little r. And if you think about it, guys, little r is changing from left to right. As you go from -r to r, the radial length of the cross sections are changing, right? So like if I were to take one of the ones that are close to the ends here, right? Little r would be different, right? So like this would be I would call this R1 and this one R2, I guess. But these two radial lengths are different. So because that's the case here, we need to come up with a function excuse me. We need to come up with a function that represents that little r. But once we figure that out, right? Once we figure that out, we can plug it into our formula here, right? We can go from -r to r. And since we know what the area of the cross section is, they're circles, it's going to be pi little r squared dx. So we just need to figure out what is little r in terms of our x. So, yeah, sorry about that. So what we're going to do is figure out a function. We need we pretty much need an r of x almost. That's going to give us the radial length in terms of x, no matter where we are on the x-axis from -r to r. So watch. I'm just going to tell you guys the trick. So from wherever you are, okay. So let's say I'm looking at this R2 value right here, right? Wherever you are, you can actually construct a right triangle. Okay, and the reason why we're going to do this here is, right, so we're going to construct this right triangle right here. And the reason why we're going to do this is because we want to figure out what this side length r is with respect to how far we go out in terms of x, right? So I can go out some x amount. I can go some positive x amount, some negative x amount, but that x has to be between -r and r, in this case, right? So if that's the case, well, we know what these measurements are, right? We know little r represents this side. X is going to represent how much you go out to create the cross section. And then the hypotenuse, if you think about it, in the context of our sphere, it's actually going to be capital R, which is a constant, right? And what we have here is Pythagorean's theorem. You guys can see that, right? We can set up an equation. Little r is going to equal what is it? Big R squared minus x squared, right? This is from Pythagorean's theorem. If I move the x squared over, right, it would be x squared plus little r squared is equal to big R squared, right? And what this does for us, remember, this is a capital R is a constant, so don't forget that. What this does for us, I forgot the square root. Sorry about that. What this does for us is this is an equation now. This is a function in terms of x and a constant. So what we can do here is now plug this in for r and then just integrate from here, because r capital R is a constant. So if those are our bounds, all we gotta do is just plug them in and we'll get the equation. So watch. And that's the hardest part, honestly, of this whole thing. So here we go. I'll write this out one more time. So we're going from negative r to r, pi little r squared, but we just said little r is equal to root capital R squared minus x squared. So it goes root capital R squared minus x squared, and then squared, right? Because this whole thing represented little r. And from here, we just integrate like we normally would. Some of you might be asking, consider the negative when we square root, because we know that in real life, you can't have negative length. So we're allowed to just kind of disregard it. Okay, we can just take the positive one, right? But from here, let's integrate this thing. So I'm going to take out the pi. Remember, negative r to r, the capital R's are constants. They could be 5, it could be 10, it could be any size sphere they want, but no matter what sphere you use, you know that radial length for the entire sphere will be the same. So this becomes r squared minus x squared dx, and we like this part. This is the integration part, right? So if this is a constant, imagine that's a constant, right? How do I integrate a constant? Well, that should just be r squared times x. And then how do we integrate x squared? That's going to be negative 1/3 x cubed. We're going from negative r to r. I know it's a little confusing because there's like little r's and big r's. Just, keep track. Once again, big R is a constant. And we just plug in the upper bound minus the lower bound, right? So we're going to go, I'm going to keep the pi on the outside. Upper bound, you get r cubed minus 1/3, well, I guess r cubed, right? R cubed on top, because plugging the upper bound, minus the lower bound. So this one's going to become negative r cubed. This should be plus r cubed over 3. Oh, look at that. It's like the same. And then we just simplify here. This becomes... this piece right here becomes, what is it? This is 3r cubed over 3. So this is 2r cubed over 3 minus, and then this one is going to look very similar. This is going to be negative 2r cubed over 3. So there's an actuality where we're adding them together. Can't forget about that pi. And then so this becomes 4 over thirds r cubed pi, which is in fact the formula, 4/3 pi r cubed. We just did it. We just proved the volume of a sphere using integration. There it is, guys. All right. So, I know it was a little confusing, right? You just have to remember that your area function needs to be in terms of x, and we had to do that little interim, piece right there. But other than that, everything else is pretty straightforward. I hope you liked it. If you want to challenge yourself, try and figure out the volume of a pyramid. I challenge you guys to try this, right? We're going to center this at the origin, try and figure out the cross section here. It looks like they're going to be squares, and try and prove that the volume of a pyramid is 1/3 a squared times h. It's fun. All right. Okay, guys. Let me know if you guys have questions about that sphere one. And yeah, I'll be seeing you guys around.